Hello, everyone. I hope you can hear me well. So my name is Stanislav Polyakov, and today I'm going to present you my talk, Machine Learning and Data-Driven Decision Making. So first of all, I want to introduce myself and also introduce the company I'm working for. So my background is actually PhD in applied physics from NTNU, Norwegian University of Science and Technology. And then I worked for a couple of years as a consultant in Meta in Oslo, also specializing in data science and machine learning. And currently I'm a lead data scientist at Coop, and I'm helping Coop to make data-driven decisions and be a data-driven company. So Coop Norway is one of the largest retailers in Norway. We operate about 1,500 stores across Norway, and we have around 28,000 employees working in 8 different chains. So we have grocery chains that you can see here on this slide, but also do-it-yourself market. And Coop is a cooperative, so everyone can become a Coop member, or also it also means that you're becoming actually a co-owner of Coop. And currently we have about 1.9 million co-owners. And I was first data scientist, joined Coop in-house team. And my mission was to bring data science to Coop. And now we have amazing in-house advanced analytics team at CoopX, a digital department of Coop, where we are helping Coop to bring machine learning, cutting-edge data science to Norwegian retail market. So you can always find me on LinkedIn and ask me questions or just contact with me if you want. So back to our topic, data-driven decision making. So why do we want actually to make data-driven decisions? The reasons are quite obvious for many people, but I think the most important that actually humans are very bad at making objective hypotheses. So we can think that something could be better, so then one thing is better than the other thing, but it's your subjective opinion. Much better is to have something to support your kind of decisions, support your beliefs, and data is the best way to do that. So this provides us more reliable way of understanding our hypothesis and also our business. But sometimes there are also very difficult questions to answer. For example, how do we measure success? So some people believe something was successful, others won't think so. So in order to answer such questions, it's better to have some data to support your decisions. And also it helps us to guard us and our business against different biases. So humans by nature are sometimes biased. And if we use some data in a clever way, we can guard ourselves against such biases. So this topic will be, in general, how we approach data-driven decision-making at Coop, what are kind of specific problems that we are facing, and in general, different kind of industry trends and different industry best practices, how to approach this decision-making, supported by data, and of course, using some machine learning technique or data science. I will start with briefly reminding you the golden standard of hypothesis testing. It's A/B testing. So many companies, best companies in the world, are always using A/B testing as the way to test their hypothesis. We also, of course, do this at Coop for our digital products, but this topic, this presentation won't be about that. So here is an example about classical A/B test that we run in our mobile app. We have 2 different options, how to change UX design Should we put logo on left side or the right side? And we test it randomly on our users. So we are making a controlled experiment to estimate the effect. Are there more clicks on the option A or more clicks on option B? We do it randomly, so everyone gets assigned different option randomly, and then there are supposed to be no biases because of that. And also, best tips is always to remember to run some AA tests when you actually don't do any changes, just to make sure that your experiment is randomized. But again, as I said, this talk won't be about that. That's just a short reminder. We can also accelerate experimentation. So, for example, you can run many parallel experiments, but then the main goal is that each experiment is independent from each another one. So if, for example, you run experiment regarding to like user engagement, like how many clicks they're doing in like coupon area, you can run also a parallel experiment, absolutely not relevant to coupons, maybe some like changing some profile settings and so on. So that's set up how you can do that. You can basically use the user ID plus some salt, take some hash over it, distribute your users into different groups, and then run these multiple experiments. Or some companies are running multi-arm bandits. But now we're getting to the point, what happens after, how to compare different experiments. So let's say you ran this experiment, you have two groups, and you want to compare these groups afterwards. So for this case, normally what you're doing is running some statistical significance test. That's our statistical test used to compare different groups. And in many cases, you compare mean values of each group, and then you find either some significance or non-significance difference between these groups. However, in many cases, running this significance test could be a bit tricky. The main problem that I face personally is trying to explain those p-values to non-technical colleagues, why like this works, why this test particular shows this significance and so on. But that's also not all the problems, because there are also about 30 plus different tests. And here is a flowchart here that should help you to choose the correct significance test for your particular problem. You can find it on the GitHub that is also presented on this slide. Very helpful. I'm not saying that significance tests shouldn't be run. In many cases, they do. We need to use them, and they actually providing the most reliable kind of answers. However, there are potentially different alternatives to this, and I wanted to discuss one of them. So here is a little article from Nature Methods, which is titled as Moving Beyond P-Values, Data Analysis with Estimation Graphics. And I think this is a very short paper that everyone should take a look into. And here is basically a tweet that says that instead of significant tests, it's better to use estimation graphics. So basically, instead of just showing like this is a control group, this is a treatment group, and that there might be some significant tests between these groups, it's much better to illustrate actually the distribution of control group and the distribution of the treatment group. And then you are plotting this distribution here that shows the distribution of, for example, in this case, is delta is the difference of means between these groups. And the question here is how this little piece of graphics is actually plotted, how we get it. And the answer for this is using Bootstrap. So it's also the authors of this paper made this package called DABEST, data analysis using Bootstrap coupled estimation. And basically it helps you to make such illustrations, but also it runs Bootstrap methods behind the scene. I'm a big fan of bootstrapping in general. I think that it's a good approach in many cases. So I will just explain and remind you briefly what is bootstrapping. So bootstrapping is a technique that was developed like in the 20th century, and originally it was a bit complicated because it takes some computational resources for you, since the essence of Bootstrap is generating many samples, for example, n Bootstrap samples, by sampling with replacement from your distribution. So for example, you have your distribution A and you are subsampling from that distribution these n different samples, but you sampling with the replacement. So it could be that the same items are actually twice or multiple times in each of these samples. And then step 2 of Bootstrap is to calculate some statistical estimator, theta, for each of this sample and get this distribution. So the beauty of this method is that you can calculate actually any statistical estimator. The problem with this method is that sometimes it could take a lot of computational power to do that. So it all kind of depends on how much data you're working with and how much like computational resources you have. But in general, I would say that nowadays with like cloud computing, with powerful hardware, bootstrapping is a very powerful technique. So just to finish regarding bootstrapping, as I mentioned, that you can compute any statistical estimator. That means when you're doing this sampling and for each of the samples, you can calculate, for example, mean. That's a very classical traditional way. Or you can calculate median or some quantiles or some other estimators like Cohen's d and so on. So why do we want to do that? Here's a good illustration on the right. Let's say we have two groups, group 2 and group 1, and those groups have the same mean values. So they are distributed around this arbitrary units, let's say somewhere around 6. So they have same mean value, but as we can see, actually, they look very different. And this is the reason why it's also sometimes important to calculate other statistical values, such, for example, as quantiles. Here we can compare different quantiles between these two different groups, and we see that actually there is a 0.77 arbitrary units difference between first quantile in group 1 and quantile of group 2. You can illustrate this in this type of plot. So you can put the difference between the quantiles on the y-axis, and then you just put the quantiles on x-axis. Why it is important, in my opinion, and why we're doing this in Coop is because, as I said, so let's say we have the same mean value. Let's say it's some transactions that people are doing. So people are spending some amount of money in the stores or on your website. So their transactions are distributed somehow. And you did some intervention, you did some treatment and had some group, let's say from group 2, now you suddenly got, after treatment, group 1. So if you compare just the mean values, you won't see any difference. You will see like, okay, so on average, transaction value are the same. But in reality, what happened? Your treatment actually changed like behavior, either of part of your users who were spending a lot, or those users who were spending very little. So this is like important to keep in mind. So even if like we don't see, if we just run a simple significance test that compare the means, it might say that the means are the same. But if we look more precisely on the distributions, we will see that actually the distributions are different, and like your for example, low spending users start spending more, or they just stop actually shopping, for example. And very good thing about bootstrapping, it also helps us to calculate confidence intervals for any of these statistical estimators. So you see that there is a dot, but it also gives you the statistical confidence intervals for this particular measurement. So this is good. And just to mention again that nowadays we have computational power. Sometimes we really work with big data and it's difficult to do these calculations. In these cases, you can try to use Poisson Bootstrap, which helps you like in a smart way to run these bootstrap techniques in parallel. So you can parallelize this on a large cluster of many CPUs. But now we're coming to essential part of my talk. Before was just refreshing your memories. Maybe you knew about A/B testing, bootstrapping. Now I wanted to talk about more tricky cases. When we cannot actually run A/B tests. There could be many differences why we couldn't do that. It could be too difficult to run A/B tests. It could be too expensive, or maybe it's even unethical, or sometimes impossible. Such examples is release of a product, or start an advertisement campaign, or change some placement of goods. The fact is that you cannot release a product and not release it. You cannot start a campaign and not start the campaign. You always have to do either one thing or another. So how can we approach this? The solution, there are multiple solutions. So here are listed few of them. You can do some quasi-experimental designs, such as difference in difference, and so on. But in this talk, in this presentation, I will focus on two methods. It's a synthetic control modeling and Bayesian structural time series modeling, BSTS. So these two solutions we are using at Coop, and I feel that they are very interesting methods that you should consider as well. They are used by some other big companies like Uber, Google, which you might find as a good indicator that these techniques of modeling works. Some authors suggest different solutions, such as having two parallel universes. In one you run your like advertisement campaign, in other you don't. But unfortunately at Coop, we cannot do that. And the same, we don't do time traveling at Coop. So let's see how we approach this. So let's say we had some metric, something that you want to measure, and then you are starting some intervention which affects kind of your whole market. Let's say you start a marketing campaign, or you start advertising a lot. So your treatment changes somehow, your metric changes somehow, but you want to see the difference of what would happen if you haven't started this campaign, what would happen if you haven't done that. So you want to model the scenario, potential scenario, what would happen if you didn't do things. And in this case, it's a red line. That's a result of modeling. And you measure the treatment effect as a difference between the actual measurement and the model results. How to do this modeling? You are using another time series, which is correlated somehow with your metric, and but it should be independent time series. And then your model is actually trying to fit your metric based on this another time series, in this case a green line, to have this red line. And this model should show you what would happen like if you haven't done this intervention. So let's go a bit into details in case of synthetic control methodology. So let's say we are running a large advertisement campaign for one of our chains, Coop Mega chain, and we want to see like what would happen if we didn't do this large advertisement. So synthetic control is a method of making this a synthetic mirror of your potential like measured time series. In this case is, for example, sales in Mega. And you mirror this using the other time series. And for example, in our case, we could use the combination of sales in other stores of other chain, which doesn't have this marketing campaign going on. So in this case, you have basically a weighted combination of control groups. And if you find these weights and proportionally, you can model very precisely sales, for example, at Mega, using the sales at extra stores, in different extra stores, with some like coefficients and some other factors. So using this, we can estimate what will happen in our like scenario, in our potential like case, if we haven't run this campaign at Mega. So the treatment effect, as I mentioned earlier, will be estimated by difference between the treatment group and the synthetic control group. So in the post-intervention period. So this is one of the ways. It's very common, I would say, in different offline A/B testing experiments. It's originally coming from econometric studies. So you can find many like large academic research doing similar approaches to figure out some effects of different government policies and so on. Another potential solution to this problem when you cannot run and not run some kind of marketing campaign or some event happening that affects your full market. So Google, as you know, is one of the largest markets for advertisement, and people are running many advertisement campaigns on Google. So they were facing the problem how to distinguish if this some increase of sales or increase of some clicks is a result of actually advertisement campaign run on Google, or is it some external factors that are impacting these sales or clicks or whatever. So they developed this package, causal impact, for doing exactly this, solving exactly this problem. It's based on the Bayesian structural time series, BSTS modeling, and it helps to explain what has been observed. So here it's similar to what I explained earlier. You have some Y metric, and then you are fitting your model to this metric until this moment where you have some intervention. And then you are looking what would happen if like your model predicts what would happen if there were no intervention. And this is actually your kind of real metric, what has happened after you started this treatment or you started something. And then you are just looking at the difference between these two to figure out what was the impact. There is a very nice talk about this causal impact on YouTube. Highly recommend it. But to finish this presentation, I wanted to say a few words about hard cases when we actually cannot see the difference. So let's say we had these two groups, control and treatment, and we followed the earlier like bootstrapping technique that I described, and we got this nice distribution and confidence intervals for this mean value. And we see that actually the difference between two groups and the confidence intervals are intercepting the zero. So we cannot actually say if it is actually there is difference between these two groups, or it's just happen like due to this randomness of this experiment. So what I want to describe right now is an approach how to make your experiments more sensitive, how to make sure that you can find the difference between these two groups. For this, I highly recommend this paper. It's was developed in Microsoft back in 2013, and it describes very interesting approaches to online control experiments, mostly for the online websites, but you can always find how to apply the same techniques to your particular case. And in this way, they are developed this methodology called CUBED, controlled experiment using pre-experiment data. So the idea behind this method is to define a new estimator, a new metric. Let's name it y cubed. And this new metric is calculated like this. You have the original business metric, y, minus some coefficient theta multiplied by x, where x is independent one-dimensional control variate. So your idea is that you want to reduce the variance of your distribution, introducing a new metric. And in the paper, they have a very nice short proof that in order to minimize the variance of y cubed, you should use theta equal to this equation, covariance divided by variance of x. And basically, it's also very easily in few lines of like simple math, you can see that the variance of new metric will be equal to the variance of original metric multiplied by this factor. And this is y minus this coefficient. And we see that actually the variance is reduced by this amount. Just to like mention that this technique is widely used in many like big companies. You can find online like blog posts from Booking.com, from TripAdvisor, and many other companies using this. So this is a nice technique how you can reduce your variance of your like metrics. And sometimes this x one-dimensional control variate could be like shifted by the mean of this x just to make it more normal, or it can be also used like historical metric values of y as your one-dimensional control variate. You can go further on the next step, and in the paper they also describe this. This you should take it a bit more accurate, since you need to be sure that all the requirements for this are satisfied. But the idea here is that instead of the linear linear reduction here, that you have just a multiplication of theta by x, you are using some regression machine learning model. And in this way, you are fitting your machine learning model, like given x, you try to fit it to y, and then you calculate this new metric as a difference between y and this machine learning model results. So we actually calculate not the difference between the original metric before and after treatment, or in group A and group B, but actually the difference between y cubed metric. And the idea behind that is that the total variance of the business metric y can be decomposed into two parts: the part that is caused by the variance of x, and the part that is actually some unknown treatment that we will see afterwards. And here is just a short result. So as we earlier saw, that the original just taking mean estimator between two different groups gave us this very wide distribution, and we couldn't actually make a definite decision out of it. But using this cubed methodology, we could control reduce our variance quite significantly, and then you can show that there is a difference between two of your groups. Very useful technique. I highly recommend it to look into that, read the papers. They're quite short and clear. And that's it, what I wanted to present for you today. Thank you very much for your attention, and I'm looking forward for your questions or anything, any connections on LinkedIn. Thank you.